All right, here we go with Unit 4 on this is Lesson 1, Proportional Relationships. This whole unit is on linear functions. So what we really got to do is we got to look back at proportional relationships. We've already talked about these a little bit earlier in the year, but they really are the basis for all linear functions. So we're going to take a quick look and kind of do a recap of what this is before we get going with this entire unit. So just remember, two variables are said to have a proportional relationship if their respective values are always in the same ratio. In equation form, if two variables are x and y, then y over x equals some constant. And this should look kind of familiar because we've talked about the change in y over the change in x. We've seen things like slope already this year. And remember, slope is always the y value over the x value and how things are changing. So this proportional relationship is going to become extremely important in terms of linear functions. So let's take a look at this first example. This is a local baker who's selling 6 bagels for $2. Determine how much it would cost to buy the following amounts and round to the nearest cent when necessary. So let's start off with an easy one here. If we wanted a dozen bagels, well, you could look, remember, a dozen's 12. So you could say 6 bagels for $2 or a dozen bagels. So you're just doubling it, so it would be $4. But how does this work math-wise? So let's take a look. So if I know that for $2 I can have 6 bagels, and I don't know how much money it's going to cost for 12 bagels, so I just set up this proportion now. I have two different ratios and they're equivalent. One of the ways we can solve this is through this cross-multiplying idea. So I have 6x equals 12 times 2 is 24. I then get x by itself. Dividing by 6 tells me x equals $4. Remember, this was the cost in the top here. This was cost. So that was quite easy. We already knew that, though. We knew if we had 6 bagels for $2, then 12 was going to be $4. Okay, but what happens when the number's not so nice? Well, you do it the exact same way. So that's why it was important to kind of be able to set this last one up. Okay, so we're going to set this up the exact same way. For 28 bagels, what do I know? I know that $2 for 6 bagels is going to equal whatever this cost is over 28 bagels. Okay, so I can do the same thing. I can do cross-multiplying. Or, remember, if I have a fraction, I want to get rid of it, I could multiply both sides by that value. Okay, so multiplying 28 times 2 gives me 56 divided by 6 equals, and these are going to cross off, leaving with just x. And 56 divided by 6 is 9.3333, and keep going with those 3's. Remember, what we are looking for here, again, was cost. So this is dollars. So let's make sure this number makes sense in terms of dollars. We have to round it. And so it would be $9.33 is the cost of 28 bagels. Okay, always make sure that your final answer makes sense in terms of the question, especially in these real-world examples. Okay, cross-multiplying also would have worked here. If you cross-multiplied, you would have had 56 equals 6x, and then I just simply divide by 6, and right here I'm exactly back to where I was before. So two different processes get the same result. Okay, let's look at an extension of this question here. Still the same question, and if C is the total cost of bagels and N is the number of bagels bought, then let's write a proportional relationship between C and N, and then solve that equation for the variable C. And then eventually we're going to graph the relationship. But let's start from the beginning here. If C is the total cost and N is the number of bagels. Well, before we had the cost in the top and the number of bagels in the bottom. So let's do that again. Let's have the cost in the top over the number of bagels. And what do we know about this? Well, we know that the cost was $2 and the number was 6 when it was $2. Okay, so let's now, it says, here's the relationship between C and N. Now let's solve this equation for the variable C. Well, what does that mean? That means let's get C all by itself. Well, one way to do that, again, we could either cross multiply, or we can notice that I have a fraction here, so I can just multiply by whatever's in the denominator. In this case is n. These are going to cancel off, leaving me with c equals 2 over 6n. You could also reduce that and say c equals 1/3 n. It's also okay to write it like this, c equals n over 3, if you really wanted to. But I think that we're going to see that it's very useful to keep it written like this, or the one above it, where you have this fraction still as part of this problem. And as you remember, when we're talking about linear equations, we always have that slope piece to them. Okay, and that slope piece is always written in terms of a fraction because we have that rise over run. So in this case, if you get rid of it and write it like this up here, it's harder to tell exactly what that rise over run is. But when it's written in this form, you can see exactly what it is. It's rise 1, run 3. So not wrong, just probably a little bit easier to write it in the c equals 1/3 times n fashion. So let's graph this relationship. Let's see. So if the number of bagels, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? And let's go up. The total cost is going to be $1, $2, $3, $4, $5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? And let's see what happens when we graph this. Well, there's a really easy way to graph this. Okay? Remember, I was just talking about this rise over run piece. So we have this c equals, so the cost is 1 over 3 times n. So let's start at 0, 0. Okay, because if the cost is 0, then I'm not getting any bagels. So we're always going to start here at 0, 0. All right, now let's take a look. Let's do the things that we know. We knew that 6 bagels right here is going to cost $2. We also knew that 12, because we figured this out earlier, was going to cost $4. Okay, is there anything in between? Maybe. Right now this is already starting to form a line. But the easy way to have done this is to start at some point we know, like 0, 0, and go by the slope. So up 1, rise 1, run 3. 1, 2, 3, put a point. Again, rise 1, run 3. 1, 2, 3. Rise 1, run 1, 2, 3. Here's another point. 1, 1, 2, 3. 1, 1, 2. There would have been one kind of out here somewhere. Okay? And this makes a straight line. Let's start it right here. Okay, like that. So as the number of bagels increase, the total cost of the bagels also increases. Okay, and that's what this line is representing here. It represents as the number of bagels increase, that the total cost is also increasing. So it says, according to the graph, C15 equals 5. This notation is very, very important. So let's just kind of recall what this means. This means the function, the cost here, when the number of bagels is 15, the cost is 5. That's what this says. Basically what it means is, when I start with the original equation, so if I wrote C of 15, is how you say this, C of 15 equals 1/3 times, you would write 15. So really the equation would read this, C of n equals 1/3 times n. Okay, so the C of n just means the function evaluated at n. So when we evaluate it at 15, that means we're evaluating this function at 15. So we go all the way over here. If this extended to 15, we go up and we go over. And notice, when we evaluate our function at 15, we get 5. So that's what this says. The cost at 15 bagels, the cost of 15 bagels is $5. Okay, so how do we interpret that? That's exactly, in terms of bagels and money spent, well, that is the cost of 15 bagels is $5. That's what that means. The cost of 15 bagels is $5. And this is on the graph how you would interpret it. You'd go to find the number of bagels is 15, and you find its cost is 5. All right, we're going to work a lot with this notation as we progress through this unit. So we'll bring it up tomorrow in class again and keep talking about it. So let's look at another example here. If a person can swim 20 meters in 14 seconds, then which of the following gives the distance d a person can swim over a span of t seconds going at the same constant rate? This is important. If it wasn't going at the same constant rate, then this problem wouldn't make a whole lot of sense. So let's see how we can do this. A person can swim 20 meters in 14 seconds. So that's what we know, right? So 20 meters over 14 seconds. Okay, and it says, which of the following gives the distance d a person can swim over a span of t seconds? So the distance is d, so that's in the top here. And the seconds are t, that's in the bottom here. So what do I want to solve for? It says, which of the following gives the distance d a person can swim over a span of t seconds? We're going to solve for d. And if you look at all of the possible choices, it all says d equals. Again, this is the output. Okay, the t here is the input. It's the independent. Okay, for a certain amount of time that passes, it will dictate how far you can go. All right, so let's see how we solve this. We can try this cross multiplying again. So I would have 20 times t, which is just 20t. And I can have 14 times d, so that's 14d. Now I want to solve for d. I want to get d by itself. In order to do that, I need to divide by 4 to undo this multiplication. And that tells me I have 20t over 14 equals d. And that is choice 4 right here. 20 over 14 times t equals d. Okay, this example is a really important one. It illustrates one of the most important useful proportional relationships. It's the distance traveled compared to time traveled at a constant rate. Think of miles per hour. We're going to do, countless times you will use this in real world applications with miles per hour. How fast is someone going, the speed at which someone's going, that kind of stuff. It's always miles per hour, and it's always the distance equals, this is what we would call the rate, this 20 over 14, times time. So distance equals rate times time. And that gives you speed. Distance equals rate times time. Okay, so let's keep looking at this. Do another example like this. Here you go. Molly's driving at a constant rate. She travels 210 miles in a span of 3 hours. So if Molly travels at the same rate, how far will she travel in 4 hours? Okay, well, what do we know? We know 210 miles over 3 hours. So here's your distance in the top, and here's your time in the bottom, miles per hour. Okay, so what were we looking for? How many hours? Remember, stay consistent here. No, I'm sorry, we're not looking for how many hours. We're looking for how far she will travel. So a distance, that's an x, and the time is in 4 hours. So use whatever strategy you would like. You can either multiply both sides by 4 here to get x by itself, or you could cross multiply. I think this time I'm going to switch it up and multiply both sides by 4. That tells me I have 4 times 210, which is 840 over 3 equals x. And when I divide 840 by 3, I get, let's see, 840 divided by 3 is about 280. So 280, and what were we looking for? This is miles equals x. So 280 miles in 4 hours. That's what she would do. So write a proportional relationship between the distance d that Molly travels and, not ands, the time t that she travels, assuming she continues at the same rate. solve the proportion for d as a function of t. This is a fancy way of solving the proportion for d as a function of t. That means d equals a bunch of stuff and it has a t in it somewhere. Okay, so first let's write this proportional relationship between the distance and the time. So the things I know are 210 over 3. 210 miles in 3 hours, and that is the distance over time. So let's use cross multiplying, or it doesn't matter. Actually, let's use where we just multiply both sides by the denominator here to get d by itself. So multiply both sides by t. So that tells me these cross off, and that leaves me d equals 210 over 3 times t. Okay, so now I have wrote the proportional relationship for the distance d that Molly travels and the time that she travels. Okay, now, and then we also just saw, so here's the proportional relationship, and now we solved it for d. So the distance equals, here's that rate, 210 over 3 times time. Question 3, what is the value of the proportionality constant? This right here is the proportionality constant, that fraction. So what is the value? Well, if I take 210 and divide it by 3, I get 70. So that's the value of the proportionality constant is 70. How long will it take Molly to travel 150 miles? Well, let's figure it out. Let's see. So we could do this a couple of ways. We could set up a proportion again. We could have said that she travels 210 in 3 hours. So 150 in x hours. Again, doing some cross multiplying, I would get 210x equals 450. Divide both sides by 210. Remember, right now we are looking for hours. Okay, so you would say x equals 450 divided by 210. You get about 2.14 hours. That would have been one way to do this. Another really kind of clever way would be to take this equation that we just found and say, okay, the distance is going to now be 150. So let's plug that in for d. So 150 equals 210 over 3 times t. Again, I'm looking for the time. Okay, so how can I solve this? Let's first, we could multiply by a reciprocal if we wanted. That's always a good thing. 3 over 210. 3 over 210. That's going to give me my t by itself over there. And this is going to tell me 450 when I multiply across over 210 equals t. 450 over 210 is the same thing I had right here. So the time again is going to be 450 over, so that's 2.14 equals t. So the time is 2.14. So two different ways to solve the same thing. If you have the equation, you can easily just substitute it in for what you know. And if you don't, you could have set up a proportion again. And you get the same result either way. All right, so let's try to graph this here. So the hours spent driving versus the miles driven. I'm going to go up by, let's go with 50s. 50, 100, 200, 300, oops, 400, 500, 600, and we'll count by ones along here. Remember, we can count by whatever we want on each individual axis. They just have to stay constant. Otherwise, we're going to force our picture to look like something it's not supposed to look like. Alright, so how can we graph this? Well, we can do it the easy way here of saying, okay, if I go 3 hours, I've gone 210 miles, so somewhere like that. Starting if I've gone no time, I've gone no miles. And then go up again 210, so it'd be at 420 and over 3, 1, 2, 3. And remember, where am I getting these numbers from? It was the slope here, this rate of change, 210 over 3. So from 420, I'm going to go up to 630, so around here, and 1, 2, 3 more hours pass. And hopefully this makes a linear relationship once again. Let's try to draw this straight line through here, and it does. We've made a pretty good graph here. So we made a linear relationship. At 3 hours, there's about 210 right here. I'll use a different color. Let's use maybe green. So at 3 hours, we were somewhere around 210. At 6 hours, we should be around 420. And look, here we go, over to 210. 6 hours, we go over to 420. At 9 hours, we should be at about 630. And that's true. So this is a pretty good line here. This would keep going in that direction. So there's our graph. And now what does the constant of proportionality represent about this graph? So in other words, what does this number and value over here represent about the graph? Well, it is the slope of the line, right? Remember, we went up 210 and over 3, and up 210 and over 3. So the constant of proportionality is the slope of the line or function. Okay? It is also, and remember this, the rate of change. It is how the y's change as the x's change. Okay, so this number that we've been finding here, okay, this proportionality constant, that's the slope. It is the rate of change to our line. So whenever we set up a proportion, like this up here, okay, we've set up a proportion, what we're really doing is we're finding the slope. All right, that's all I have for today. Come to class tomorrow with questions. We'll work more on this, and especially on that function notation I was showing you earlier, where I was saying the C of 15 equals 5. We'll talk a lot more about that tomorrow in class. All right, we will see you then.